Hello, I'm Catalin Stoean. I'm an associate professor at the University of Craiova, Romania, and we will have a presentation about histopathological image classification.
I'm Daniel Lichtblau from Wolfram Research, and I will be giving the second half of this presentation.
Hello, I'm Catalin Stoean. I'm from University of Craiova, Romania. I'm an associate professor there. I'm not a physician. I'm working in computer science, but a few years ago, I've been involved in a project that contained also physicians and pathologists. And I have to thank the previous speaker. She introduced us to this world so that we don't have to provide so many details. What we wanted to do, among other goals, was to classify colon cancer histopathological images into 4 classes. This is the data set we mainly worked on. So we had 4 classes back then: normal, grade 1, grade 2, and grade 3. When I got involved into this project, my background was pretty much related to evolutionary computation and machine learning, but more related to numerical data, less to images. So I was actually hoping that there is there somewhere possibility to transform the images into numerical vectors and then just use a classifier, and my job would be kind of done. But unfortunately, I did not really find an easy way to do this. So I had to do it the hard way. At first, how these images were obtained? We had larger images from which some crops were extracted. The larger images contained also boundaries between normal tissue and cancerous tissue. So there are in this data set the light and the instrumentation was similar for the normal tissue and some parts of the cancerous ones. So every time I think there are tissues that resemble very much in light only between normal tissue and cancerous tissue. So of course the normal tissue look like Tesita said, quite all right. I mean, the glands are very circled. There is not this chaotic organization as we can see in the other grades of cancer. Okay, so as I said, our main focus was to work on this data set. It contained images with magnification of 10 times, and we had 4 grades there. But then we wanted to actually validate our approach, and we tried other data sets too. And among them, the Glas and BreakHis. For these, we had only 2 classes. We did not have 4, so it's only normal and cancerous. And we could say that actually BreakHis represents 4 different classification problems, because it contained 4 different data sets of different magnification levels: 40 times, 100, 200, and 400, and each one of these was actually larger than the other data sets we had. So this is a very large data set that is available. Actually, all these data sets are available for download if someone wants to go and test them. So what was my approach? I actually followed it. This happened around 5 years ago, so I followed the usual guideline. I mean, I had to pre-process the images, to segment, to look for some components in these images, then extract some features, and then after this we end up with too many features, so we have to select out of these features the ones that are important, and finally apply a classifier in order to reach the conclusion, to reach the class of an image. For each step, there are many options. So many options for pre-processing, many options for segmentation, for feature extraction, feature selection, or for diagnosis. So we kind of tried some of these options. We stopped at some options. I was interested back then into finding the glands and finding the nuclei. And for these components, I went to compute morphological features like area, perimeter, and also went to other features that involve the topology of these components. So that would be the Voronoi diagrams and Delaunay triangles. And for all these, of course, again, area and perimeter and different dimensions, we end up with 76 measurements, having also average, median, minimum, maximum, and so on. So different statistics about each measure. And after this, tried several, so this is some kind of history, what I did before meeting Daniel and using Mathematica. So all these were done in OpenCV with C++, a lot of work. I went over and do some feature selection then. Tried several options for feature selection there too. The one that proved to be the best one was actually using a genetic algorithm to select, because I told you I have, as a background, I have evolutionary computation. This is what I've been working on, so of course I had to use a genetic algorithm after all. And as a classifier, the best classifier, I tried several, and support vector machine appeared to be the best choice. By the way, I did not mention the classification in the best situation was somewhere almost 84% for this data set that contained 4 classes, which for me and for the physicians was, for them it was not such good news, but for me it was. I mean, I was quite, I thought it was a good result for a 4-class classification problem. When presenting those results, I had the opportunity to meet someone that was using deep learning, and we started a collaboration. We tried to apply this convolutional neural network for our data set, which led to better results, somewhere around 91 after tuning a lot the data set, but still not overfitting. Very recently, back then I did not, I was not quite used to code in Python and using convolutional neural networks, so I did not try more than just parameter tuning. But this year I tried ResNet. By the way, this result was not even published. ResNet 50, so transfer learning and fine tuning, and the result moved even to 95%. So, which was, of course, very, very nice. But now turning back, when I when I met Daniel at a conference, he was presenting, I was standing in the room, and he was presenting something that I was hoping to see from the very beginning. He had a method that transformed images into numerical vectors. So from each image, he would obtain some vector of about 300 values. So I thought this would be wonderful for my project. So I would just transform the images, and I could classify them afterwards. I talked to him. He, of course, wanted to work together, and he did with this classifier. He did better than what I did with the 7 steps classifier. So the result was somewhere around 88–89%, which was quite okay. I mean, I was happy with it, but. Then we had the opportunity to use Mathematica. I mean, we had a lot of options there. There was this function that I found really magical, classify, which actually accepts anything, accepts numerical data, accepts images, even sound files. And it could classify images. So we tried several options here, many classifiers for these images. We did not know back then exactly what the classify function did, how it did. Actually, only yesterday we found out at this conference that behind it, it has, so to share the secret with everyone, it has a convolutional neural network behind. So it actually produces 1,024 features. So the features that are produced by AlexNet convolutional neural network are extracted and fed to the classifier next, so the classifier can be applied on these numerical values. And the results from these were even better than what Daniel presented. Some of them were not better, but some were better. And somehow we managed to combine these results. Among these classifiers, we had the random forest, naive Bayes, k-nearest neighbors, support vector machines, logistic regression, neural network, so simple neural network, and the method that Daniel presented and caught my attention. This Fourier trigonometrical transform plus principal component analysis. Actually, we, as Daniel will present next, he will present the second part of this presentation. He will actually show that although this FTT plus PCA did not lead to the best results overall, it had a very important role in leading to a better results than what we previously obtained.
Okay, I think, yeah, I'm mic'd up. Thanks, Catalin. Okay, so to save a bit of time, we've cut a little bit of information about the details of this FTT plus PCA. I'll just say in brief, it's 2 steps of dimension reduction. We use some kind of Fourier trig transform and take the low frequency components. That's step 1. And then we flatten these smaller dimensional matrices into vectors. We do this with, so each image now becomes a vector. And we do something, principal components, like we subtract the mean. I think we take a singular values decomposition, and we drastically cut the dimension there. And we then feed the resulting vectors into the nearest function in Mathematica. So it's another KNN type of approach. However, it behaves very differently in terms of results for our purposes than the KNN method for classify, so that it turns out to be useful in its own right. Oh, okay, so here's the results we got over, I think it was, we did many randomized splits of 2/3 training, 1/3 testing, and the means for the averages for all of these and the other statistics you can see. And so the FTT plus PCA comes out basically in the middle and actually very close to KNN in terms of the mean, but well, I'll get to more about that later. The SVM and logistic regression did the best. The neural net was also somewhere in the middle, although we probably could, I mean, we did the most naive thing possible. Method goes to neural net, and something goes to either quality or speed, performance goal, I guess. And we didn't try to get fancy with the neural net. If we had it, we probably could have made it do somewhat better. Okay, so the next thing is to combine these into an ensemble that is sort of a voting scheme, so that you can get better results than you could from any individual classifier. And so what we did was we'd split our tests up, and we did a bunch of runs where we would tune to get good weights for each classifier, so that these classifiers deliver probabilities and or surrogates for probabilities, and what we want to do is weight these and sum them, and then the highest sum determines what grade of cancer, 0 through 3. The highest sum wins for our classification. Okay, so we wanted to optimize these, and we did. We used and minimize in Wolfram language with differential evolution as the method. There's a reason for that, which I will probably just have to gloss over. So yeah, I think I skipped a slide. I think there's another slide that's in hiding somewhere here. But rather than go through the details, I'll just convince you that it's sort of tame by showing the code. There won't be a quiz. But, and yes, it probably looks a bit cryptic, but it's short, and the reason it's short is because it actually isn't all that complicated. So what we're doing is, because the actual outcome is discrete, 0, 1, 2, or 3, we subtract, we take the difference between actual and expected, our mistake, in other words, and we square it. I think that's what we're doing here. But yes, because we want to really penalize errors that are off by 2 or 3 more than errors off by 1. And that turned out to be a pretty good objective function to minimize. And we used differential evolution because my experience, at least, and it's fairly extensive, is that it's a fairly robust optimizer when your function, your objective function, is discrete valued. Okay, so we did 20 of these splits, and we did some careful looking and some programmatic analysis to determine which gave the best weights. But in fact, the weights that we got tended to be pretty similar across these 20 runs. Okay, and so what were the weights? Well, the random forest is 6%, and KNN is fairly large, and so is FTT plus PCA, despite the fact that they're from the same general family of methods. And the neural net gets a very low weight, and so does naive Bayes, despite the fact that they did, the neural net was a middle pack performer. SVM and logistic regression, the two best performers individually, are getting decent weights, but not nearly as large as the largest of those. So why is that? Okay, so we use Cohen's kappa coefficients because that's a reasonably good way of assessing correlation when you're dealing with categorical data. We use this, and we find that the Fourier transform plus PCA method is more decorrelated from the others than any other pairings. And so, you know, it has the lowest coefficient in every row, except of course for the last row where we're comparing it to itself. And so what does this mean? It means that this method is making its mistakes in different places, and by and large, from the other methods. And so when it's wrong, the others tend to outvote it anyway. When it's right, it's heavier weighting tends to overcome the, you know, the fact that the others several of the others might be wrong. Okay, so it's an offset. It's a nice balance. Okay, hello. Okay, so here's the results. My gosh, did I show the results for immediate treat? I didn't. I skipped right over. Okay, so the results are we get 98% correct on this four-way classification. That's not bad. And most misses are off by one, and the bad news of, you know, there was one person who was perfectly healthy who got a grade 3 report, and you can die of a heart attack as easily as cancer, so maybe that wasn't such a good thing to tell that poor patient. But, you know, so there's room for improvement. But as confusion matrices go, that one, there's a lot of values that are either 0 or very close, and most of the mistakes really were between category 1 and 2, or level 1 and 2, and level 2 and 3. Okay, for these other tests, Glas, they're broken into 2 sets, and we did 95%. It's a small test set, so 95% and 90%, or it's like, you know, 19 out of 20 and 18 out of 20. BreakHis is hard, and so our next goal really is to do better on that. Why is it hard? It's because all of your tissue samples are from tumorous tissue. It's just benign versus malignant, but there's no normal tissue. And some of the benign, a certain class of those, these are breast cancer or breast tumors, a certain class of the benign looks very similar to another class of the malignant. So this is a hard test set. By the way, we did this without changing the weights that we had optimized for immediate treat. So, you know, it may make sense for us to re-optimize for this type of tissue. Okay, so I'm, I guess, getting pretty close to out of time, but I think I'm also close to out of slides. Yes. Okay, so what did we do? It's a one-step classifier, no segmentation, no Voronoi, no hardcore image processing or computational geometry. Some of my colleagues might be disappointed to hear that, but sorry. The pathologist just, you know, they want a diagnosis. So this is based on machine learning, and it's end-to-end. It was optimized for a particular data set. It does tolerably well on others. I say so, no tuning necessary. Yeah, take that with a grain of salt. Maybe we should retune a bit for different types of cancer tissue. Room for improvement, yeah, there's plenty. BreakHis, even though we're getting 80 to 90% on that test set, we could do better, I think. And so this might involve different machine learning methods and maybe going harder at it with a neural net that might be better suited for this particular class of images. Other things I've been thinking about and getting ready to work on, color deconvolution, because the slides are not evenly colored, the H&E staining, and deconvolution tends to offset that. So a pathologist really needs those stained slides, but a neural net might actually get, you know, overly focused on the amount of color when that varies just because of the way the tissue sample was done. Other things related use rotations and of both training and test images to sort of eliminate edge or reduce edge effects where tissue boundaries kind of do funny things. And I would like to find a better dimension reduction scheme, but I don't have one yet. Okay, so I think that really was the last slide. It really was. Okay, thank you very much.